Right now, if you are driving a car, you are sitting on top of, well, thousands of literal violent explosions happening every single minute.
Yeah, it's when you actually step back and think about it, a four-stroke internal combustion engine is basically just a metal box containing these continuous detonations.
Exactly. So, why aren't you getting whiplash? Why does the car just glide smoothly down the highway instead of violently jerking forward with every single boom?
It's an incredible illusion of modern engineering, really. We totally expect our machines to deliver this steady, unbroken stream of power, like water pouring perfectly out of a pitcher.
Right.
But the reality inside the crankcase is the absolute definition of cyclic chaos. I mean, force is being delivered in massive, instantaneous spikes.
And smoothing out those spikes is exactly what we are focusing on today. Whether you are an engineering student cramming for your dynamics finals, or you're just, intensely curious about how the physical world hides its complexity from us, our mission is to unlock the secrets of mechanical stability.
We are taking a deep dive into how engines regulate their own violence, essentially.
And we have some incredibly detailed source material guiding this exploration today. We are looking directly at the ME 503 Dynamics of Machines lecture notes, specifically focusing on the causes of speed fluctuation and flywheel analysis.
Which are fascinating topics.
Truly. And a huge thank you to Dr. Chandan Chattoraj, professor in the Mechanical Engineering Department at Dr. B.C. Roy Engineering College, BCREC, in Durgapur for providing these really comprehensive notes.
Yeah, they are fantastic. We're going to break down the mechanics of energy storage, map out the visual energy cycles, demystify the core mathematical terminology.
And run through a specific scenario, too, so you're totally ready to ace these concepts.
The best place to start, honestly, is by clearing up a foundational misunderstanding. Before we even touch the math or the physics, we have to establish what a flywheel actually does.
Right, by looking at the classic trap that catches almost everyone learning this for the first time.
Yeah.
Because I have to admit, I fell right into this trap myself. I was looking at Dr. Chattaraj's notes, and I'm genuinely stuck on something right out of the gate.
Oh, yeah.
Yeah, so the notes talk about flywheels smoothing out speed by managing energy. But a few pages earlier, we talked about governors doing the exact same thing.
Right.
If they both regulate the speed of an engine, aren't we just using two different words for the exact same job? I feel like I'm missing the core distinction here.
You are definitely not the only one. That is a notoriously common exam trap, which is why the notes explicitly contrast the two right away. If you write that they do the same job on a test, you will lose points immediately.
Ouch. Good to know.
Yeah, the distinction really comes down to the time scale and the actual mechanism of control. A governor acts essentially like a thermostat for the engine's overall power supply. It controls the mean speed by physically adjusting the fuel.
Okay, let me see if I have this. If you were driving up a steep hill, the engine works harder and the overall speed drops. So the governor senses that drop, opens the throttle, and literally dumps more fuel into the cylinder to bring the average speed back up.
That's the mechanism at play, yeah. The governor is reacting to external loads, adding or reducing energy from the outside source, meaning the fuel tank. Because of that, it operates intermittently.
Got it. So it's not always doing something.
Exactly. It only steps in when the engine is running away from its target mean speed.
Yeah.
And importantly, it relies on mechanical linkages that inherently involve frictional losses.
But the flywheel, on the other hand, can't access the fuel tank.
No, it has absolutely no influence on the fuel. A flywheel cannot maintain a constant speed if your car hits a hill and the overall external load changes.
So what does it do?
A flywheel works continuously on a microscale. It manages the fluctuations that happen within a single cycle of the engine, and it is a pure, frictionless exchange of kinetic energy.
Wow.
Yeah, it takes a violent spike of energy from an internal combustion explosion, stores it as rotational momentum, and then just bleeds it back out fractions of a second later when the engine has no power.
So, to use an analogy, if the engine is a corporation, the governor is like the CEO.
I like this.
The CEO watches the broader market, the hills, the external loads, and adjusts the overall operating budget.
Right.
But the flywheel is the company accountant. The accountant can't, print more money. They just manage the day-to-day cash flow, catching the big revenue spikes so that the company doesn't bounce its paychecks on a slow Tuesday.
That perfectly frames the dynamic. The CEO adjusts the mean, the accountant handles the cyclic fluctuations.
Okay, that clears up the confusion for sure. But it brings up a much more difficult problem, I think.
Which is?
Well, the accountant has to balance the books, meaning the flywheel has to catch the exact amount of excess energy the engine produces. How do engineers actually know what that excess is going to be? You can't just, guess how heavy a steel wheel needs to be and hope for the best.
No, definitely not. You have to map the energy output. To do that, mechanical engineers rely on a specific visualization called the turning moment diagram, or TMD.
The TMD.
Yeah, understanding machine dynamics fundamentally requires being able to read this graph.
So looking at the visual in the notes, I see torque, which they call the turning moment, basically the raw twisting force plotted on the y-axis.
Correct.
And the x-axis represents the crank angle, meaning the physical rotational position of the engine shaft. So we are looking at a literal map of how much twisting force is happening at every single degree of the engine's rotation.
And the curve on this graph is rarely a flat line. It's an absolute roller coaster. The first critical insight from the notes is that if you calculate the total area under that roller coaster curve for one full cycle, you find the total work done by the engine.
Oh, that makes sense. And if you take that total work and divide it evenly across the degrees of rotation, you can draw a perfectly flat horizontal line straight across the middle of the graph.
Exactly.
That flat line is the mean torque. It's what the engine's power output would look like if it were as smooth as water pouring from a pitcher.
But because it's not smooth, you get these massive deviations. Once you draw that flat mean torque line, you immediately see pockets where the actual torque curve spikes aggressively above the mean and deep valleys where it drops way below.
And the shaded area in those peaks above the line, that represents the excess energy, right?
Yes. The engine is producing more twisting force at that specific millisecond than the machine actually needs.
And that excess energy has nowhere to go. I mean, if the flywheel doesn't absorb it, that spike of force just shakes the machine to pieces.
It would literally tear itself apart.
Let's map this directly to the real world because Dr. Chattoraj's notes highlight two really fascinating cases. Case 1 is a fluctuating input with a constant output, like a four-stroke internal combustion engine driving a steady generator.
Right, and the TMD for a four-stroke engine is incredibly dramatic. An engine requires 2 full rotations of the crankshaft, so 720 degrees to complete one power cycle.
Okay.
And that cycle is broken into 4 distinct phases: suction, compression, expansion, and exhaust.
But only one of those strokes actually generates power, right? The expansion stroke, when the spark plug fires and the fuel actually explodes.
Think about the physics of that for a second. During expansion, the turning moment spikes massively above our flat mean line. The engine is producing far more energy than the generator needs at that exact moment.
Right.
But during the suction, compression, and exhaust strokes, the torque curve dips entirely below the line. The engine isn't just failing to produce power. It is actively consuming energy to suck in air, compress the fuel, and push out the exhaust gas.
Oh, wow. So without a flywheel, the engine would literally stall after the explosion because it wouldn't have the momentum to push the piston back up to clear the exhaust.
Exactly. The flywheel absorbs the violent spike of the explosion, stores it as momentum, and physically drags the engine through those other 3 dead strokes. It is the literal definition of a mechanical battery.
That is wild. And case 2 flips that dynamic completely, which is arguably even more interesting from an engineering perspective.
Oh, absolutely.
Case 2 involves a constant energy input, but a wildly fluctuating output demand. The primary example the notes use is a punching machine, or like a metal press, powered by a standard electric motor.
Let's put you, the listener, in the shoes of a factory engineer for a second. You have been tasked with setting up a machine that stamps metal parts.
Sounds easy enough.
Right, but the catch is, stamping metal requires a colossal, instantaneous spike of power, but only for a fraction of a second when the die actually hits the steel.
Just bam.
Bam. The rest of the time, the machine is just idling, waiting for the next sheet of metal to slide in. If you don't use a flywheel in this design, you are in serious trouble.
Because you would have to purchase a motor capable of delivering the maximum required force for that punch.
Exactly. You are talking about a massive, incredibly expensive, high-voltage motor. And the worst part is, it would just sit there operating at 1% capacity for 90% of the time, just waiting for that split-second demand. It's wildly inefficient.
But when you introduce a flywheel into the system, you completely alter the math. You don't buy the giant motor. You go to your boss and say, hey, I'm buying a much smaller, cheaper motor that supplies a low, continuous average power.
Brilliant.
And you let that small motor spend all its time gently spinning up a massive, heavy flywheel. Then, when the punch needs to happen, the flywheel dumps all of its stored kinetic energy in a fraction of a second to smash the metal.
And the little motor barely even notices the power spike.
It's so elegant.
You are letting the mass of the wheel do the heavy lifting instead of the electrical grid.
Yeah.
It dramatically reduces the required motor capacity. But this requires extreme precision. You need to know exactly how heavy that wheel needs to be.
Which means we need to transition from visualizing the energy to calculating the actual physical dimensions of the wheel.
Let's do it.
I'm looking at the terminology section of the notes right now, and there are 3 crucial coefficients. The first is the coefficient of fluctuation of speed, denoted as Ks or sometimes Cs.
Right, KES is simply a ratio. It takes the maximum fluctuation of speed. So the difference between the absolute fastest the wheel spins and the absolute slowest it spins during a cycle and divides it by the mean speed.
Okay.
It gives engineers a standardized percentage of how much the speed is bouncing around. And its counterpart is the coefficient of steadiness.
Which is just the exact reciprocal of Ks, right? 1 divided by Ks. So if your speed fluctuation is a tiny fraction, your steadiness is a massive number.
Precisely. The third term bridges the gap between speed and physical force. The coefficient of fluctuation of energy, Ke, or C.
Heat.
This looks at the raw joules of energy bouncing around.
Yeah.
It's the ratio of the maximum energy fluctuation to the overall work done per cycle.
Having these terms defined is great, but the notes really push toward a massive simplification, which I love. They walk through the derivation of what is essentially the master design formula for a flywheel.
But before we look at the simplified version, we have to look at the raw physics of kinetic energy.
Okay, hit me with it.
The maximum fluctuation of energy, which we call delta Ke max, equals 1/2 times I, times the quantity of the maximum speed squared minus the minimum speed squared. So delta Ke equals 1/2 I times omega 1 squared minus omega 2 squared.
Okay, that formula should actually sound really familiar to anyone who took high school physics because it is just the standard kinetic energy formula, 1/2 mv squared, but adapted for rotational movement.
Exactly. We just calculate the energy at the fastest speed and subtract the energy at the slowest speed. The difference is the excess energy the wheel absorbed.
The variable that trips people up here, though, is I, the mass moment of inertia. The formula is I equals mk squared, mass times the radius of gyration squared. I see the letters on the page, but what is k, the radius of gyration, in actual physical space?
Think of a figure skater spinning on the ice. When they pull their arms in tight to their chest, they spin incredibly fast.
Right.
When they throw their arms out wide, they immediately slow down. Their overall mass hasn't changed at all, but the distribution of that mass has.
Oh, I see.
So the radius of gyration, kg, is just a mathematical representation of how far away the mass is from the center of rotation.
Which is exactly why flywheels often look like old wagon wheels
Oh.
with spokes and a massive, heavy outer rim.
Yes.
You don't want a solid disc. You
Yeah.
want all the heavy metal pushed as far out to the edge as structurally possible. Because in the formula, I equals mk squared, that distance k gets squared.
Exactly.
Yeah.
Pushing the mass to the outer edge gives you exponentially more energy storage capacity without having to add a ton of dead weight to the whole machine.
The geometry is just as important as the mass.
Totally. Now, going back to that master formula, engineers rarely start by knowing the exact max and min speeds. They usually start with a requirement. They know the required mean speed, and they know the allowable fluctuation, Ks.
Right.
So through algebraic substitution, the long kinetic energy formula condenses into something beautifully simple.
Let me find it in the notes. Ah, here it is. It breaks down to this. Delta Ke max equals I times omega mean squared times Ks. So the maximum energy fluctuation is just the inertia times the mean speed squared times the speed fluctuation coefficient.
It's so clean. If you calculate the energy spike from your turning moment diagram, and your factory requires a specific Ks so the machine doesn't rattle apart, you can instantly solve for I.
And once you have I, you know exactly how to design the radius and mass of your wheel.
Precisely.
Let's put this exact logic to the test. Let's walk through the specific problem provided in Dr. Chattoraj's lecture notes. If you are listening and prepping for a test, try to track this logic with us.
It's a great exercise.
So we have a flywheel with a mass of 2 kilograms. Its radius of gyration, Rk, is 1.2 meters. During operation, its speed fluctuates, dropping from a maximum of 460 RPM down to a minimum of 435 RPM.
And we need to find the energy released by the flywheel.
Exactly.
Okay, the first step is calculating our mass moment of inertia, I's. Since we have the mass and the radius of gyration, we use I equals mk squared.
Okay, so that's 2 kilograms times 1.2 meters squared. 1.2 squared is 1.44. Multiply that by the mass of 2, and we get an I of 2.88 kilogram meters squared.
Perfect. Now for the speeds. We are given revolutions per minute, 460 and 435. But our formulas require angular velocity, omega, which is measured in radians per second.
Right, this is a classic unit conversion hurdle on exams.
It trips up so many students.
To convert RPM to radians per second, you multiply by 2 pi and divide by 60 seconds. So omega 1 is 2 pi times 460 divided by 60. Omega 2 is 2 pi times 435 divided by 60.
Awesome. With I's calculated and our speeds converted to radians, we plug it into the raw kinetic energy formula. 1/2 times 2.88 times the quantity of omega 1 squared minus omega 2 squared.
Okay, crunching the numbers.
If you run those numbers in a calculator, what do you get?
Well, this is where we have to pause and look really closely at the provided notes because there is a fantastic lesson hidden here for you.
The rounding thing.
Yes. In the handwritten calculation on the page, the final answer for the energy released works out to 353.33 joules. But up at the very top of the page, the typed answer key states the answer is 353.59 joules. There is a 0.26 joule discrepancy.
And that small fraction of a joule is entirely due to rounding during intermediate steps.
Yep.
If you convert your RPM to angular velocity, and you round that decimal off to 2 places before you square it in the final equation, you lose precision.
It seems so minor, but in a real-world scenario with a massive industrial engine, compounding rounding errors like that can scale up to a miscalculation that causes a crankshaft to vibrate and, well, shatter.
Definitely. For an exam, the pro tip is to always double-check your professor's rounding policy. And honestly, just let your calculator hold all the digits of pi and the intermediate fractions in its memory until you hit that final equal sign.
Such a good tip. Precision really matters. And speaking of precision, the final piece of the notes provides this incredible cheat sheet.
Oh, the summary table?
Yeah, it's a summary table of industry standard values for the coefficient of fluctuation of speed, KS. It totally grounds all this theory into tangible design constraints.
It really does.
Yeah.
The table shows how wildly the math changes depending on the industry. For instance, the recommended KS for industrial pumps is between 15 and 130.
Which seems pretty loose, right?
Well, a pump is just moving fluid. If your water pressure pulses slightly with each stroke, the system can handle it. The flywheel doesn't need to be massive to enforce a really strict tolerance there.
That makes sense. Moving up the precision ladder, machine tools require a KS of 140 to 150. Generators in automobiles are much stricter, demanding 1100 to 1300. But then at the very bottom of the table, we hit aircraft engines.
The recommended speed fluctuation for an aircraft is astonishingly tight. It's 11,000 to 12,000.
Wow, that means the speed is allowed to deviate by barely a fraction of a percent.
Well, the stakes dictate the tolerance, right? At 30,000 feet, vibration is a catastrophic enemy.
I can imagine.
Cyclic chaos causes metal fatigue, which causes parts to fail midair. An aircraft needs near-perfect steadiness, which means the flywheel system has to be highly optimized to absorb almost every microscopic deviation on that turning moment diagram.
It's just brilliant. We've traversed a massive landscape of mechanical engineering today, honestly.
We covered a lot of ground.
We unpacked the fundamental difference between the thermostat-like control of a governor and the pure momentum-based energy storage of a flywheel.
Right.
We visualized how machines literally swallow their own violent energy spikes through the turning moment diagram,
And we broke down the geometry of the radius of gyration.
showing exactly why pushing mass to the edge of a wheel allows a tiny motor to power a massive metal punch press. And finally, we saw how the math scales from a sloppy water pump all the way to a commercial jet.
It's all connected. The underlying logic is universal.
Yeah.
These purely physical spinning wheels have been stabilizing our mechanical infrastructure since the dawn of the Industrial Revolution.
But the craziest part to me is that this isn't just old school heavy industry tech. We think of flywheels as like ancient wagon wheels.
Sure.
But right now, the most advanced high-tech server farms on Earth, and even experimental nuclear fusion reactors, are using magnetically levitated flywheels spinning in absolute vacuums to store massive amounts of energy with zero friction.
Oh, it's incredible technology.
It really leaves you wondering, as we try to balance the massive, invisible digital energy grids of tomorrow, how much will we rely on the oldest mechanical battery ever invented?
It's a powerful thought to end on, because the physics of momentum never really go obsolete, do they?
No, they just get faster. Thanks for taking this deep dive with us today.